So Matteo Mucciconi from Singapore is going to talk about orthogonality of spin q-Whittaker polynomials.
Thanks, Guillaume, and thanks everybody for being in the audience and to the organizers for inviting me. This conference is very nice. And I will speak about this result. And before we get into the technicalities, I want to tell you why I care about this result. So in 2018 or 17, Alexei visited Tokyo, and that was at the beginning of the PhD. So Sasamoto told me, which was my PhD advisor, told me, Alexei is coming, but like a few hours before, and so he said, okay, you should ask some questions. So I pulled up archives, that was his last paper, and the last paper was the one where he defined these polynomials, and I was like, okay, let me read this paper very quickly. And I realized, okay, he doesn't prove orthogonality, because I knew, I mean, I was very young, maybe I didn't know any of this big results, but I know that special family of polynomials are orthogonal, right? Ask Wilson, McDonald, Hermite, right? And I ask, are these polynomials orthogonal? And he said, I don't know. I don't know if you remember.
I don't remember.
But, and then I felt like, then I felt like, okay, I wasted a question. I don't know how the conversation went, but this was the first question. Okay, now the answer is yes. But okay, let's. This is the story, and now we get into the technicalities. Okay, so the first part of the talk is going to be about definitions. Hopefully we define the main objects. So we define some vertex weights. So we have vertex weights. So we have a vertex and some edges entering this vertex, and to each of these edges we associate certain values n, k, m, and l. These are integers, and to such a vertex we associate a weight, which is going to be of this form, is the Q1 weight. There is a delta factor k plus n equal to L plus n. So entering edges are equal to outgoing edges, and there is another delta factor that this number m needs to be less than or equal than the number of particles entering from below. And then there are some factorized expression, x times b, so to the power m times x b. Maybe I feel like, can you see this? Not all of them. X times b, q-Pocamer symbol, n minus m, a divided by x, q to the power n, a, b, q, n, and then there is a q binomial factor, n, m, q. So I imagine that some of you know, most of you, all of you know about the meaning of these terms, but the structure is not going to be very important, so I prefer to leave the weight like this. So this is, we call this w, x, it depends on three parameters, x, a, and b, of this vertex, and takes this form. In particular, it's a polynomial in x. Although here x appears in the denominator. So having defined this vertex weight, so we define, so we prepare a lattice model. In the following way. So we have our, okay, maybe I mean. We have our grid, and we associate to each vertex. So here is I, j, a set of parameters in the following way. So each each row gets an x parameter. So for example, maybe the top row gets x1, the second row gets x2, x3, and so on. The first column gets a parameter, let's say b1, b2, and so on. And finally, we associate the third set of parameter, which is this our a's in the vertex weights, in a diagonal fashion. So there is going to be a first diagonal, there is going to be a second diagonal, there is going to be a third, where is it? There is going to be a third diagonal, and so on. And to the first diagonal, we associate the weight a1. To the second diagonal, we associate the weight a2, the weight a3, and so on. For example, to this vertex here, we are going to associate the weight w. So this is w x2, okay, x2, a2, because it's the third diagonal, a3, v2, sorry. Is that clear? How the weights are assigned?
The expression for the weight, so n is less than m, and
no, sorry. M is less than n. The number of particles that exit from here needs to be. Okay. So this is our lattice model, and now I need to do another lattice model because we define the polynomial as partition functions of a certain lattice model. So we define the definition. So you pick set parameters. Let's say, let me use this notation. Xn will denote a set of n parameters, n variables. So, okay, maybe I need to add underline, and then an and bn being, I don't know, cn, with some condition maybe. And for partition and for lambda, a partition, lambda 1, larger or equal than lambda n, we define set the polynomial f lambda, which is going to be a polynomial in x in n variable, depending on parameter an and bn, is going to be the partition function of the following vertex model. So this is an n by n grid where each vertex is decorated as in this picture, and we fix empty boundary condition here and empty boundary condition here, some boundary condition which are free here, and on the top we are going to set the number of exiting arrow from the first column is going to be lambda 1 minus lambda 2, which is a negative number, and so on, lambda k minus, okay, in this case it's lambda n, because lambda n plus 1 is going to be 0 by assumption. So the partition function means that, okay, at each vertex we associate a vertex weight with parameters as described here, and we have to sum over all of the possible configuration. For example, for the case where there are two paths going out from here and one path coming out from here, one possible configuration might be this. So something like this. And notice that as a result of this delta factor here, there could be automatically no path exiting from this location. Okay. Okay. So this is the definition of the polynomial. So these are called what I call them. Okay, let me abbreviate as QW, but with a caveat. This is a la. let's say the people that have defined this, Borodin, maybe Wheeler, but also Grothendieck. So Borodin and Wheeler defined the case where all the weights are equal to each other, and Sergei defined the case where there is also this extra. When Alec, Alexei, and Sergei define the case where there is this extra diagonal inhomogeneity. Okay, so what is interesting is that some remark here at this point. So these polynomials here are going to have nice property as a result of the fact that these weights these weights are chosen in this particular way. But one might ask, like, what is interesting about these weights? And I think the nicest property of these weights was found in a paper by Grothendieck in some year 24. That the vertex weights W with some parameters are morally square roots of an R matrix. Square roots of an R matrix. Okay, what does it mean? It means that if there exists an isomorphism, so usually you have the R matrix is an intertwiner between tensor product of two modules, but in this case, the square root part comes from the fact that the tensor product is isomorphism between tensor product of modules is taken in a strange way. So this is going to be a Verma module of UQSL2 hat. He actually also proved it for SLN, I think, but for this case we don't need this generality. So the Verma module comes with a parameter, and in this case we take the parameter to be 1 over A1A2 with A1B1. And since this is a module of an affine Lie algebra, it also comes with a spectral parameter, which in this case is A1 divided by B1. And then we have to take the tensor product of V, 1 over the same parameters, but with the index raised, A2 over B2. And it turns out that this tensor product is going to be isomorphic to a tensor product with which we don't simply swap the two vector spaces, but we actually swap these parameters in a funny way. And let me see if I can make it correct. 1 over A1 B2, A1 over B2, yes, only the B's are swapped. And here we have V 1 over A2 B1, A2 B1. So only the B's have been swapped. And so this isomorphism there exists an isomorphism, and then the matrix element of this isomorphism are given by these vertex weights with an appropriate choice of parameters x, a, and b. I think you have to take, you're going to take x, a, and b appropriately. So if you repeat this procedure once again, you swapping the a parameters instead of the b's, you are going to get your R matrix, and this is let's see, a2 b2, a2 over b2, tensor product of 1 over a1 b1, a1 b2, right? And so composing twice in some way, when changing the parameters, the vertex weights w, you get the R matrix, but there is something in the middle. And this something in the middle is the explanation why, in my opinion, is the explanation why you have this extra. When you consider the intertwiner of this Verma module, you get this special extra choice of parameters, which is absolutely uncommon, in my opinion, for solvable lattices, where usually you have one spectral parameter for the horizontal direction and one spectral parameter for the vertical direction. So this is not my result, but
a couple of questions. So first of all, in the paper of Grothendieck, he says inhomogeneous. Are they the same?
they are inhomogeneous because, yeah, it's self-contained. I mean, there are the variables x's, but then you see that vertex weights depends on the location, and this is where the inhomogeneity word comes from.
It's the same object that you're defining.
This is the same object, yes.
And then the second point is in the first delta that you wrote, I think in the model of Alexei, usually is k plus n is equal to L plus m.
Okay, there is a typo. Thank you. Otherwise, it wouldn't make sense. And cancels. Okay. Anyway, so the meaning is that the number of arrows that enters is equal to the number of arrows that go out from above.
Yeah. Does this depend on an, or like?
It depends on an. It depends on an. Simply because if you take only one vertex, so you're gonna have something like entering and then immediately going up.
Seems like you know that nothing enters from the bottom and nothing leaves from the right.
Enters, and that's all here. For example, in this example that I drew, maybe this guy could have gone here and pick up the nth diagonal.
Okay, maybe.
So in the simplest case, there is only one vertex.
Yeah.
There is A1,
yeah,
X1, B1.
Yeah.
So depends.
But it seems like the A only appears like if n and m are both 0, then the A goes away, or maybe I'm missing something.
If n, so m, so this is n.
Right.
So as soon as you have some outgo. Oh, maybe
I'm missing something, but like it seems like the bottom and the right are 0. So.
Right, so maybe you're right. So the thing is that maybe there is. So it should depend when they enter. Okay, there is some weight here. It depends when they.
We can talk about that.
Or maybe I did some wrong parameterization. I think it's correct, but so okay. Anyway, this an is about to disappear, so let's see. So what they proved then using, maybe I remove the type. What they proved is that so using these special properties, special features of the vertex W, some theorems are possible. Theorem, which so Borodin, Grothendieck, and Grothendieck, 24. So Fs, so the Fs are symmetric in the set of variable xn. And moreover, they, for example, let me record one property, and they satisfy the following summation identity. So A n, B n, and then you have some constant psi lambda, which depends on the A m, B m, and then you have another polynomial. Y m b m a m. So this is a factorized expression. So this is equal to a fully factorized expression, which I am going to write as HQ of xn ym, then HQ of am b an bm divided by HQ of xn bm, and finally HQ of an ym. So you have to think of this. I will define what is HQ. but you have to think of this as a sort of a series of products of Q deformation of beta functions. So where, let me define this product, where HQ of xn ym, so this is equals to product I going from 1 to n, product j going from 1 to m, 1 over xi yj to infinity. So this is a Q gamma function, or very close to be a Q gamma function. And so this is a fully factorized expression. So and the remark is that what I find nice about this result is that actually the symmetry is reasonably easy with ideas that were already available a few years ago. But proving this summation identity, where in particular this sets of parameters is swapped, this uses a Yang-Baxter type identity, which was proven from purely, let's say, representation theoretic methods. Is a consequence of Schur lemma instead of computations. But okay, so this is the result, but there is a plot twist at this point. So, and the plot twist is that these polynomials are not very good. So let me, these polys are not very good. So I don't want to say that they are bad, but they are good, but not very good. It's okay. Because I think that maybe to receive the final legitimacy, they need to be orthogonal. Allow me this narrative. And in fact, so this is the definition, which I think is solves the issue. So let me define. Definition. The family of polynomials, which humbly I will define with a lowercase f. Is it clear that this is a lowercase f, lambda, xn, a, n minus 1, b, n minus 1. So this is simply the polynomial we have defined before, xn, an, bn, where we set an minus 1 equal 0, an equals 0, bn equals 0. So, okay, so this is my contribution. I set one parameter to 0, and apparently this seems completely trivial, but this operation actually is going to endow these polynomials of a list of properties that are highly desirable from my point of view. Okay, so for example, let's enumerate a series of, is it clear what is the definition? So we are just simply killing two of the parameters. So let's say some additional properties, some initial properties of the Fs. So first of all, it's not true that we are losing generality, because we can recover the Fs from the from the big Fs from the little f. So maybe one initial property is that the family Fs, f of lambda of x's, xn, are symmetric in the variable xn and satisfy nice summation identities, which trivially follow from setting some parameters to 0 there, and satisfy Cauchy identity, for example. Okay, so this is the first property. The second property is that you can actually recover the f, the capital F. So we have f lambda xn an, an bn. So this is equal to f lambda x n plus 1 an bn, where xn plus 1 equals 0. So if you allow one extra variable, you can fall back into the polynomials defined before by simply setting one variable to 0. So in reality, we are not really losing generality if you really cared about that couple of parameters here. Okay, so these are very simple properties. Let me just, since I want to give extra, well, legitimacy to these polynomials, let me say, what do they specialize to? So what are some simple cases? The following things are going to also hold for the capital F. So these are not special properties of the polynomial little f. So special cases, 3. Special cases. So okay, so let me have so this is f lambda, and here I'm going to write the name, and here I'm going to write parameters. So if you set q equal to ai equal to bj equals 0, so these specialize to s lambda, which are known as Schur polynomials. So if you set q equal to ai equals 0, so you keep only one family of parameters, the b's, for example. You could keep the a's. So these become capital G lambda, known as Grothendieck polynomial. Is it correct? Grothendieck polynomials. So Grothendieck polynomials, there are several family of polynomials called Grothendieck polynomials. So these are the symmetric Grothendieck polynomials. There are also polynomials that are non-symmetric called Grothendieck polynomials, and these are a special case of those. Okay. I think I remember what I want to write. So if you keep q positive but only set ai equal to bj equals 0, so you get some polynomials that have been defined before, so the q-Whittaker polynomials. If you only set one set of parameters to 0, for example ai equals 0, you get a family of polynomials f lambda, which actually were studied for the first time, I think, by Sergei in his paper, and he called them interpolation q-Whittaker. And it's called interpolation q-Whittaker because they solve nice families of interpolating condition. Namely, they have zeros at specific location on the plane, and they show that these are the only polynomials that satisfy this condition plus some additional property. Then when we take the limit q that goes to 1, but let ai equal to bj equals 0, we get something called the psi, which are the Archimedean Whittaker functions. So there is a scaling involved in this case, and maybe let's keep lambda as a parameter. And finally, if we let q ai bj go to 1 at the same time, we get some family of polynomials, which maybe I call f lambda. The partition lambda also needs to be rescaled, which we call spin Whittaker polynomial. And the result that I'm gonna discuss above, so this is point 3 of the enumeration of properties of the f's. The results that I will discuss below are going to be known for the cases of Schur q-Whittaker and Archimedean Whittaker, but they are going to be new, although some of these results will be pretty basic, but they will be new for Grothendieck and this other family. In particular, I was quite surprised that the results, such as the orthogonality that we'll discuss in a second, are not known even for this family of polynomials, which is quite popular.
So the Grothendieck depends on n variables where n is also a number. Well, but in n variables and n parameters.
Yeah. So these are called inhomogeneous Grothendieck polynomials. So I don't know, they are called I call them in this way, some other people call them in this way. So I can give the definition, but maybe there is no time. So Okay, let's start enumerating non-trivial properties. So number 4. So this is something already non-trivial. So the f lambdas are eigenfunctions of q difference operators. So first of all, define the operation tqx, which takes a function f of x and returns f evaluated at qx for any function of the variable x, and let, so definition, this is called the q shift, and then you define a family of q difference operator, which are going to depend on n-1 parameters, defined as follows. So you have a summation I going from 1 to n, a certain product, let's say R going from 1 to n-1, there is a 1 minus xi br times product I is already used, j going from 1 to nj different than I of 1 over 1 minus xi xj, and finally tq xi. So this function, so this operator takes a function of n variables and applies the sum. Each of the sums has a product term and has a q shift term in the ith variable, and there is another operator which defines similarly. So there are two families of q families. Yeah, there are two families of q difference operators, d and d bar. D depends on the parameter b's, and d bar depends on the parameter a's. And in fact, I promised you some eigenfunction relation. Then, or theorem, let's say theorem. Then we have d bar a n-1 of f lambda xn a n-1 b n-1. This is equal to q to the minus lambda 1, and then the same polynomial, f lambda xn and so on. Okay, maybe I should start dropping this these two things. And similarly, there is also another eigenrelation for the second. Well, I define it first, class of difference operator, f lambda. Okay, there is a q to the lambda n, f lambda. Okay. So this is I think it's some nice property. And well, I don't know if we get there, but usually these q difference operators are of interest, are useful in the connection, have some sort of probabilistic connection because the polynomials f are going to be related to the solvable theory of the q1 tensor, which was defined, for example, I think yesterday by Alexandre. And this q difference operator tells you that the q moments of the q1 tensor have some nice property. So 5. So you can extend the polynomials f lambda to Laurent polynomials. So there is something called shift property, which is that f lambda of xn is equal to x1 xn f lambda minus 1 to the n xt. Right? So you can factor out a product of this form, which I maybe start calling capital Xn, at the cost of reducing your partition, lambda 1 minus 1, lambda n minus n minus 1. So this property seems trivial, but for the case, it's actually quite important, because for the case of it's fundamental. I don't know if it's important or not, but it's in the case of sure polynomials, this property corresponds to the fact that the sure polynomials are, let's say, characters of the SLN, but you can make them a character of GLN by adding a determinant representation, and the determinant representation is the product of eigenvalues. And so the sure polynomials might become characters of GLN, allowing them to be Laurent polynomials, for example. So then 6. So for example, these properties are not enjoyed by the original polynomials. So I'm starting to accumulate some evidence that this slight modification makes them better. So 6. So maybe I should come back to this later. But for example, there are connections to integrable probabilistic model. For instance, lambda n is equal in distribution to the nth particle of the Q1 taser. It should not be too much surprising, because the vertex weights which are used to define these polynomials are exactly the one entering in the definition of Q1 taser, but still is a non-trivial result. And in particular, is not true for this polynomial. So it's not just because of the weights. And then finally, we justify the title of this talk by, let's say, just give it a theorem. So all of these are some results. So first we have to say that something is orthogonal. We need to define a scalar product. So define the scalar product on L2 of the torus in n dimension, n copies of the torus. So the scalar product is the following. Maybe it's not going to fit. Maybe double. Fg. So Fg are two functions, regular functions on the torus. And we take their integral, f of zn, g of zn bar. Here we conjugate every number of this list. There is a measure, zn, a n minus 1, b n minus 1, dzn. Okay, so it's the integral is on the torus. So we're integrating over n variables, and now we have to define who is lambda n, delta of zn, a n minus 1, b n minus 1. It's going to be equal to, okay, so hq z bar n a n minus 1, hq z n b n minus 1, hq a n minus 1 b n minus 1 times what? Times the product r going from 1 to n minus 1 ar br q infinity times 1 over n factorial product I different than j zi over zj q infinity and times product are going from 1 to n of 1 over 2 pi I z I. Okay? It is what it is. Huh? Okay, so this is the measure on the torus.
What is HQ?
HU was defined before, and it's a product. HQ is the product of Q gamma functions. So there are two sets of variables. So you take the product of two gamma functions for each pair of in the sets of variables. Okay, so the theorem is not finished because this is just a definition of the. Should I do? Maybe I can do it there. Then nothing. Then we have that f lambda, okay, of some variables zn a n minus 1 b n minus 1 scalar product f mu z n b n minus 1 a n minus 1. So also in this case this sets of parameters is swapped. This is equal to delta mu equal to lambda, so they are orthogonal with respect to this this product, and we can also find their L2 norm, which we call, let's say, Cn of lambda, where Cn of lambda is a product for k going from 1 to n minus 1 of ak bk q infinity q infinity ak bk q lambda k minus lambda k plus 1, and then q lambda k minus lambda k plus 1. Okay, so they are orthogonal, and we also can calculate their L2 norm. Like I said, okay, I erased all the particular cases, but I want to say that this result was known, like I said, in all the cases where the parameters a and bj are 0, but it's new for all the rest of the family of polynomials. In particular, when we set q equals 0 and we let maybe we make only one set of parameters survive, we get an orthogonality result, which is new for the Grothendieck polynomials. And I don't know, I was surprised to have found such it was not known in literature, but in the Grothendieck case, let's say comment. In the Grothendieck case, a similar result was in a paper by Motegi and Sakai, where instead of this orthogonality, they have a sum over beta roots. I'm not sure which result implies which other, but they look reasonably close. But also they don't deal with inhomogeneities. So anyway, I want to just cite their work in the Grothendieck case. Motegi and Sakai, let me say, Motegi Sakai, I think in 2013 have a similar looking result.
And Matteo, the reason why you have this factor depending only on a's and b's inside the delta, the denominator of that thing.
Yeah. So these are, of course, they don't change. They don't depend on the z, so they are just constants in the integration. Just like this is an integration, this is a constant in the integration. One can offload them onto the L2 norm.
Yeah, but
If
is
you
there a
want.
reason why you put them there? It's
Because this is balanced. So when you deal with Q series, you want Q series to be balanced in the sense that if you take some Q goes to something limit, you don't have to renormalize it. For example, if you take a look at this, this is a balanced product because you can maybe take some Q goes to one limit in this case, and nothing is diverging. Well, everything is diverging, but they are all going to infinity at the same time, so or to zero at the same time. So it has a reasonable limit. Okay, so this is the result. Let me say why people like that don't.
I have another question, which is you said that B equals 0 would give you interpolation q-Whittaker.
Mhm.
So if I put A into 0 on top of that, I would have somehow just by the name expected to get factorial sure or double sure.
So what do you do?
So I mean, you just told me that. I mean, earlier you said that if you set A to 0, you get interpolation q-Whittaker, right?
Yeah.
So just by the name, I would have thought that if you on top of that set q to 0, you would get interpolation sure or factorial sure, something like that. Is that just by the name? I would have thought that. Is that somehow wrong?
No, so the interpolation.
Yeah. Okay.
So the interpolation property is different.
I see. Okay.
The dependence of the set of interpolation points on the parts of the Young diagram is different.
See. Okay.
There.
Okay, maybe let me just make one more comment. So if you set AI equal to if the product of AK and BK is equal to Q, so this the L2 norm becomes 1, which suggests that this simplification might bring something nice, but I don't know. So
What if the product of A5 and B5 is equal to 1? Because then you have the same constant in the delta and in the C, right? Which is the diagonal products of A's. So what I'm asking is if that thing vanishes. It seems that, I mean, both sides vanish, but you can cancel it and they still make sense. Is this some nice case?
right, there is this in the numerator. So I think this numerator is going to destroy your 0 in the denominator. So sorry, it's not really clear, but this is the first line. So if A1 B1 is 0,
Yeah.
so here we have something in the numerator that tends to 0. Sorry, no, A1 B1 equal to 1. In the numerator we have something that goes to 0, but here we have something in the denominator that still goes to 0.
What about the C of lambda?
C of lambda is simplified.
Oh, same thing.
Because this is gonna be Z, this is gonna be a Q infinity, and this is gonna be nothing, it's just 0.
Unless some difference of lambdas is 0. In that case, it's not going to cancel.
That case is not cancel.
But that
Lambda 1.
that probably forces something in the partition function that will prevent that. I don't know.
Yeah, it's a reasonable question. Okay, let me say, I don't know. So, and then I want to switch. And I want to say something like why this. I feel pretty. I mean, I feel a little bit optimistic on some potential applications of this result. So orthogonality in my mind is related to certain results that have appeared in the study of these solvable models, and is related to something that I think Pierre calls BCR integral formula. So I will explain why. So we have said that lambda n has a probabilistic interest, right? If you know lambda n, course, this model has been solved in other ways, but I want to just say. So, for example, the probability that lambda n is equal to a certain number L, it can be written as a summation for lambda over the set of partitions with lambda n equal to L over f lambda xn a n minus 1 b n minus 1 times let's say f lambda yn yt, let's say bt at times a constant, let's say times a constant times c lambda. I called it psi lambda. Right? So let's define this probability measure, and I claim that if I define this probability measure on the partition, well, okay, this is not a probability measure, so we have to take normalize it. But so this is some interest in probability, and in fact it describes the law of the one particle in the Q-Hunt set. So using orthogonality, using not only orthogonality but also all of the properties, which properties? Let's say 5 and 6, and also the Cauchy identity. We get we can compute something that is on the other sheet. Okay, I don't have time to do all the calculation, but so we can compute some quantity which is known to have some nice property, which is the Q Laplace transform of lambda n. So this is some generalization of the exponential, and this is going to be equal. So this is using all of the properties that I enumerated above. This is going to be equal to this thing that I am writing, I from 1 to n minus 1, q infinity, a I b I q infinity times the product of a bunch of HQs, in the numerator, times okay, so times I don't want to. Right, times a bunch of other factors and a bunch of other HQs. Okay, so yeah, okay. But so what I want to say is that this, if I had time to expand, open up this scalar product, this is an n-fold integral where it starts as 1 over n factorial times the integral over the whole the torus, and this is a generalization of a formula by which was done by Borodin, Corwin, and Remenick for the log gamma polymer model. For the partition, for the free energy of the log gamma polymer model, well, it's Laplace transform, and then it was also used by myself, Sasamoto and Imamura, for other contexts in other models. But okay, so orthogonality seems to be related to the derivation of such a formula. And the reason I am talking about this is that in the derivation of such formula, there is no, so usually when one computes the moments of gamma and beta functions, these are diverging, so the derivation of formulas is hard to justify. But taking this approach, using the orthogonality results, this summation does not need any justification because all the quantities involved are going to be non-diverging. And a similar result, and then maybe let's move to question. A similar result, and then maybe let's move to question, is that if I had time to expand, open up the questions section. So, questions. So the first question, let me dovetail into the first question, is a similar BCR, let's call it integral formula. Was found by Ledoussal, okay, let me and Thierry in 2015. For the model that they introduced, which is called log beta, inverse beta polymer, or the polymer model. But this inverse beta polymer model, although was introduced 10 years ago, still remains highly conjectural. In fact, I don't think there are many rigorous results about it. Certainly, Tracy-Widom fluctuations, for example, are still conjectural. Maybe I'm not sure if there are any developments on this. And one of the reasons why this is still an open problem to study rigorously this model is because the usual ideas, which is approximate, which is by using special symmetric functions, or by using Q deformation, studying the Q deformation, and then maybe solving the Q deformation and taking the limit, they don't work, because in fact it was pointed out in this paper that if there exists a Q deformation, it maybe it's not a probability measure, it probably is a negative measure. And so this is an interesting model, but it makes perfect sense. In particular, I think it has some legitimacy because it's like the most general solvable polymer model, but also it's the most general polymer model which has factorized invariant states. So it's interesting. And since they find a BCR formula, and I just showed to you that BCR formulas are connected to orthogonality of families of symmetric functions, it was giving me some hopes that these orthogonality results might have some application in this case. But I have not thought about this for the moment. Questions? I think I'm out of time. So yeah, okay, let's keep one question, and maybe you have other questions.
You showed the first order difference operators. Do you believe there are no higher order ones, or are they just too complicated to be found? Yeah.
So some natural generalization of this first order difference operator fail to work because they don't commute. So you can write those difference operators as a conjugation of the McDonald difference operator by factorized expression. If you do the same thing for a higher order cases, it turns out that they don't commute. But if you factorize them, okay. Short answer: I don't know how to come up with nice higher order Q difference operators. Yeah. In fact, one question could be like, are there difference operator, or maybe does there exist a McDonald extension of this, because they are gaining more and more legitimacy, but we don't know.
Nagging question. So if you take your vertex model, it has a degeneration where you get this beta polymer with these diagonal homogeneous Sergey's paper. If you set parameters to 0 as you do, does it make that polymer model to get your lowercase f functions? Does it look any nicer at the level of the polymer degeneration, or does it really just look the same?
I think so there are several ways of. So I think Sergey did not use such a thing. He did not say that that the polymer model is distributed as as a McDonald type measure. I think he just studied the moments and come up with some nice formula and analyze the formula. So in that, if you take the polymer model by Sergey, well, I think you can set any parameter like you want. But I think that the polymer model coming from this measure is going to have all of the right parameters. It's not going to miss anything. I'm not sure if this answers your questions, but
Maybe the question was
but the thing is that the way, so I think Sergey studied a model, but he approached the model not through the lens of McDonald measures, but he just used the Hecke algebra to pull out some integral formulas for the moments. Another way would have been to first say that this polymer model is distributed like a McDonald measure, which is not a result that I know. I mean, that I know from his paper, and then study the McDonald measure. But he studies directly the polymer measure. I think the polymer model. I think.